Let's do a quick way of seeing how a current source driving an RLC circuit in parallel um, will behave to a step current, and will the system be over, under, or critically damped. All right. So really we can use our impedance, right? And just notice that in this region, right, the current isn't changing. So it's kind of DC. Well, that means the frequency is 0, right? Over here, we can see that it's acting DC again, after a long time, right? So we call that frequency 0. Now in the middle, this is changing quite a bit, and you can think of that as the high frequency rate regime. And if you haven't had the Laplace transform, that's okay. Just think, I have an infinite slope change. I have an infinite change here. The slope is infinite, right? So that means things are changing in an infinite way, which sounds like high frequency, right? It's just very intuitive. So if we look at the device, right, the impedance for the resistor is R, the inductor is S times L, and capacitance is 1 over SC. Well, in these two regions, right, a long time before the step and a long time after the step, the frequency is effectively 0. So R is R, the inductor is a short, right, and the capacitor is an open. So let's just redraw it. Before the step, the current is 0, it's acting DC, the resistance is the resistance, and I've just drawn a short for the inductor, and the capacitor is open. Well, the current is 0, so there can't be a voltage increase across anything, right, because it's 0. But notice that this short, even though there was a current, all the current would go through here and not through the resistance. So this output voltage would be 0. And after the step, yeah, the current is not 0, right? But again, it's acting like a DC, so it's shorted. And so whatever current there is would ideally all go through that loop, and it wouldn't build up anything across that resistor, right? So now that we got that, what about whether the system is over, under, or critically damped, right? And, that over, under, and critically damped is just something for a second order system that we give a special name to, right? But if you kind of put an input into a system and it just keeps oscillating back and forth, right, for a long time, that's underdamped, right? If you kind of input the system and it slowly and smoothly approaches some final value, you'd call that overdamped. And if kind of the same thing happens, that's critical damped. Now, the thing is unless the frequency part of the system is the same, it's kind of hard to tell the difference between an over and critically damped system for looking at it in time. In the frequency domain, right, it's actually easy. So anyway, but let's start it. So let's look at this system with 0 current, right? So I can assume there's some kind of, initial condition, but it doesn't matter right now. So I'll set this equal to 0. Well, while you set voltage sources to 0 with a short because they have 0 impedance, right, current sources has infinite impedance. So to set this current to 0, I just take it out of the system, right? And then I have these 3 parallel elements, and yeah, I just write current voltage equation at node 1, right? And it might seem odd to write it like that, but just remember you could have initial conditions here. All right? So those currents sum to 0. Then we use Ohm's law, V1 divided by R plus V1 divided by SL plus V1 divided by 1 over SC. Now we can get rid of this V1 because it can't be 0, otherwise the problem makes no sense, right? So if we go to the next page, right, now I got 1 over R plus 1 over SL plus 1 over SC, right, equal to 0. Now we're almost there, but that form doesn't help us. you really need to have things in a proper polynomial form where everything is a power of s to the 0, 1, or 2. So to make that happen, you multiply it by s and divide by c, so we get this equation. Now, yeah, that s is normally a real plus an imaginary. In your circuits book, it could just say it's a function. But the thing is what's really easy to do is, now that we're in this kind of frequency domain, to tell whether it's over, under, or critically damped, I just need to tell the roots. Well, you use the quadratic equation, right? Minus 1 over RC, plus or minus, right, B minus 4A. Right? And you can do the substitutions yourself. But you don't need the rest of this. Right here tells you what kind of roots. So if 1 over RC squared is bigger than 4LC, I'm going to get plus or minus 2 real numbers, and I will get plus or minus 2 real roots. That's overdamped. That's just the definition. Now, if these two are equal, I get plus or minus 0, but there's 2 roots there. They just happen to be the same thing, right? And that's critically damped. But now, if this is less than this, well, that negative sign is going to give me a complex number. And you should just know that anything with a complex in it tends to oscillate, right? So that would be underdamped, right? Now, this is just a down and dirty way to do it. If you really need more, you know, the 98 textbook is on loan in course reserves. There's plenty of resources about underdamped systems online. You should have seen it with like a pendulum swinging in differential equations, right? So those are places to look or to kind of remind yourself where you've seen it. But really, working in the S domain here, right, and setting the input voltage or current, the input to 0, right? All I have to do is kind of find the impedance picture, and I can tell what this system is going to do. But it's not going to tell, so the thing is, right, if I come back to the first part, right, it's going to, the current through the inductor is going to start at 0 and it's going to end at 0. But it's not 0 in between. If it's underdamped, it's going to oscillate before it settles to 0. If it's critically damped, it'll go up and come down faster than if it was critically damped, underdamped. All right. Now there's a lot in there right now, but basically, you know, just a rough sketch. If it's underdamped, it would do this. Critically damped might do that, and overdamped might do something like that. This is a rough sketch. To actually plot those out takes a little bit more effort. But if you can tell right away what kind of system it is for not very much effort. Okay?